Okay everyone, welcome again, and what I'll discuss here once I set this up it's better is I'm going to talk about excitation-contraction coupling. Now I've just done this video before and it refused to save it for me, so I'm going to have to do it again, so I'll try not to go too fast or get too angry with things as they go. So excitation-contraction in muscle, we have to start with excitation and then finish with prior to contraction. So the starting point is excitation, and we all know with muscle, excitation comes from the motor neuron. And so we need a motor neuron and we need a neuromuscular junction, so we need the motor neuron to connect up with the muscle, and that's here. This happens at the end plate. And then of course we know the muscle membrane continues on and plunges down to where we have the T-tubule, which is a continuous part of the muscle membrane. Another important part, of course, associated with this is the sarcoplasmic reticulum, which contains calcium. We'll talk about that a little bit later. And finally, of course, the muscle needs to contract. So we have our thick filaments and our associated thin filaments in between, held together by the Z lines, forming the sarcomere. So I think that's pretty much all we need to start off with. So excitation-contraction coupling, let's start with excitation. So we have our nerve, our motor neuron, a myelinated axon, branches out to the muscle fibres and forms these motor end plates. So when the depolarization reaches the end of the axon here, the axon terminal, it causes the opening of voltage-dependent calcium channels. Calcium comes into the axon terminal and increases its levels, and the increased calcium levels cause vesicles, which contain the neurotransmitter, amongst other things, acetylcholine, and these vesicles will fuse to the membrane and you'll get the release of acetylcholine into the neuromuscular junction. So acetylcholine in the neuromuscular junction, we need that, and what it will do then is the acetylcholine will bind to the receptors that we find within this motor end plate area here at the neuromuscular junction. To maybe build this up a little bit, we can look over this side. Okay, here's our muscle membrane, here's our receptor, acetylcholine receptor, a nicotinic receptor it is. It has two binding sites for acetylcholine, so the molecule will bind on these sites, and when it binds, it opens up the channel. And when this channel opens up, you get the inward flow of sodium ions, therefore elevating sodium concentration inside there of the muscle membrane, and a little bit of flow of potassium out, but not much, so it's negligible. So let's forget about it. Let's not make it more difficult than what we have to at this stage. So as the sodium ions come rushing in, it produces what we call a miniature end plate potential, which really you can associate with the graded potential that we've talked about earlier with nerve transmission and the production of action potential. So if this is our muscle or motor end plate membrane potential, and this is time, acetylcholine binds, sodium ions come in, and you produce a small depolarization. Okay, so that's all well and good, but does this small depolarization do anything to stimulate muscle contraction? Well, not by itself, obviously, of course. It's not great enough. And also, it's limiting. It's a receptor-operated channel. What type of channels do we need to produce depolarization? We need these ones, voltage-dependent sodium channels, and what you find is surrounding the motor end plate are these voltage-dependent sodium channels. And like any voltage-dependent sodium channel, in order to activate them, you need to reach threshold. How do you reach threshold? By producing all of these miniature end plate potentials at all of these, or most of these nicotinic receptors that are activated by acetylcholine. So what happens is you release the acetylcholine, it comes binds all these different all these nicotinic receptors, sodium ions come in, you produce lots of these miniature end plates potentials, and this will cause threshold to be reached at these voltage-dependent sodium channels, and you'll produce an action potential here in the muscle membrane. So that's important. What happens to this acetylcholine that's released? Well, it is very quickly broken down by an enzyme that we find called acetylcholine esterase. So therefore, if you want to maintain the depolarization, if you want to produce more action potentials here at this sodium channel, you have to keep on releasing acetylcholine. And in order to do that, you must continue to stimulate the nerves. So your motor areas of your brain have to continuously send messages down the axon to keep the muscle stimulated. Alright, so we've produced an action potential, so what happens next? Well, you get a depolarization moving down the T-tubule. So it moves down the T-tubule, and therefore there must be something that it changes. And what does it change? It changes a specific channel. And this is a calcium channel, a voltage-dependent calcium channel, also known as the dihydropyridine receptor. And so when this is depolarized and threshold is released, the dihydropyridine receptor opens. Now obviously you're going to think, well cool, calcium comes rushing in and all this. No, it's not quite. The calcium doesn't come from here that stimulates muscle contraction. This receptor actually is coupled in some respects, I guess you could say, to another receptor that is found on the membrane of the sarcoplasmic reticulum inside the muscle, and this receptor is known as the ryanodine receptor. And so when this channel is activated and opens, it opens the ryanodine receptor channel by this sort of functional togetherness, I guess you could, or coupling of the two. And when the ryanodine receptor channel opens, it's a calcium channel. Now calcium levels inside the sarcoplasmic reticulum are very high compared to the myoplasm of the muscle. It's about 1,000, 10,000 times, a huge amount. So calcium ions come rushing in, and therefore this increases intracellular calcium concentration dramatically, enough to produce muscle contraction. Now the production of force by the muscle via this is another story, and I'll put a video up about that later, maybe tomorrow or something. So it's another story. So we won't worry about that. But we can see now excitation occurs here, contraction occurs here. We've looked at excitation-contraction coupling. What is this? The depolarization of the nerve terminal causes calcium to cause the acetylcholine vesicles to fuse, release the acetylcholine. It produces all these miniature end-plate potentials on the nicotinic receptors, which in turn will cause the voltage-dependent sodium channels on the muscle membrane to reach threshold, producing action potentials. This produces a wave of depolarization that opens the dihydropyridine receptor on the T-tubule, and when this opens, it in turn will open the ryanodine receptor, which will therefore allow calcium to rush out of the sarcoplasmic reticulum, increasing calcium levels in the muscle. And it's this increasing calcium levels inside the muscle that is going to produce contraction. Thank you.